Hello friends, welcome back to my channel. So today we will going to cover vibrational spectroscopy. For this we need IR spectrum, infrared spectrum, and we can also call it as infrared spectroscopy. So we are talking about the vibration of the molecules. In previous video we have seen how rotational spectroscopy works, and we use microwaves for this purpose, and for vibrational spectroscopy we will use infrared radiations. So we will cover physical part of this spectroscopy in this video, and we will also take PQR spectrum. Then in next video we will cover its organic part. Right. So first, the most important thing is that we have to consider the vibration of the molecule first as a harmonic oscillator, simple harmonic oscillator. What is its means? According to harmonic oscillator, we will consider that vibrational motion is following simple harmonic oscillations. The bonds are perfectly elastic in nature, means when they will vibrate from its position, they will come back to its position back, and their bond length will not change in that process. So the energy of the variation in the energy with the bond length is given by a perfect, or you can say perfect parabola like this. This is the graph between energy and the internuclear distance and harmonic oscillator. This should be like this, right? So, and the energy of this oscillator is given by n plus 1 by 2 h nu in joules, right? And the frequency is given by 1 upon 2 pi under root of k over mu, where k is the force constant which depends upon the bond strength, and mu is the reduced mass, right? And most of the time, as we have seen in case of microwave spectroscopy also, that energy is represented in terms of centimeter inverse, means we have to convert this energy and this frequency in the form of wave numbers. So what we can do, we know that the speed is equal to nu into lambda, frequency into wavelength. So if we divide this nu by c, we will get 1 upon lambda, and 1 upon lambda is nothing but your wave number. So if I will divide this part and this part by c, means E over c n plus 1 by 2 h nu over c, I will get, and I will take this h from this position to this position, then I will get energy in the form of wave number, right? And it is represented in the form of centimeter inverse. So we will use this formula most of the time, and from this formula we can calculate that energy, 0 point energy. 0 point energy means this n can have values from 0, 1, 2, all the integer values, right? So 0 point energy means when we have n is equals to 0 at the ground state, this energy will become E is equals to half h nu. This is called as your 0 point energy, in terms of joule, right? And if you want to find out this energy in terms of centimeter inverse, it will become 1 by 2 nu bar. This is 0 point energy in terms of centimeter inverse. Then if I want to calculate the difference between two successive energy levels, this is for harmonic oscillator, right? This is all about harmonic oscillator. So suppose this is n is equals to 0, this is 1, so I can calculate the energy E1 minus E0. You should write epsilon 1 minus epsilon 0. This is the energy difference, and the general formula is, suppose n plus 1 minus n is equal to mu bar minus, right? I have just placed the n plus 1 label here. Now I can calculate this value, and it will come equal to nu bar centimeter inverse. So this is the energy difference between two successive energy levels. So suppose for 0 point energy, the energy is 1 by 2 nu bar. For the next level, it will become 3 by 2 nu bar. If I will plus nu bar in it, it will give me 3 by 2. Then for next level, for n is equals to 2, it will become 5 by 2 nu bar. Means this difference in energy level is same for harmonic oscillator. This is same. This energy gap is same for all energy levels. This point is very important because in case of rotational spectroscopy we have seen that this gap is increasing, right? But in this case this is constant for harmonic oscillator, and the selection rule is n is equals to plus minus 1, plus for absorption, minus for emission, but this is only 1 for harmonic oscillator, simple harmonic oscillator. Simple harmonic oscillator means bonds are perfectly elastic in nature. There is no change in their internuclear distance or bond length. So this is all about all the important points about harmonic oscillator. Next we will take Enharmonic oscillator. So now you can easily recognize that Enharmonic oscillator is the real situation, real bonds. They are not perfectly elastic. Means there is some enharmonicity in them, and that will lead to change in their bond length. Means if I will draw a graph between energy and the internuclear distance, and if I am vibrating the molecule with much higher energy, this bond can break. This graph is known as Morse curve, Morse potential energy curve, and this distance is called as DEQ, which is called as dissociation energy, and the distance from n is equals to 0 to this level is called as D naught, right? This is your internuclear distance and this is your Morse potential curve, and according to this curve the energy and the relationship between energy and dq is given by an equation. You can memorize this equation. E is equals to deq 1 minus exponential to the power a x whole square, right, where x is equal to r equilibrium, the distance, the internuclear distance at equilibrium, and minus r, and deq is dissociation energy, and a is a constant, right, and its formula is 4 pi square mu xe mu bar c over h, where xe is enharmonicity constant, right, and the formula of energy will change when we are considering enharmonic oscillator, because the energy value is calculating considering this dissociation energy. They will use this we can use this equation in Schrodinger equation, and then we will have this formula of energy n plus 1 by 2 mu bar. This is for harmonic oscillator. We have to subtract n plus 1 by 2 whole square mu bar xe, right, this is in centimeter inverse. So you have to memorize this formula where n can have values 0, 1, 2, 3 and so on. The 0 point energy can be calculated from here, and it will become, when I will place the value of n is equals to 0, it will become 1 by 2 nu bar minus 1 by 4 mu bar xe. This is called as 0 point energy, and this is important, right? You should know what is the 0 point energy of harmonic oscillator and for enharmonic oscillator, right? Then next is this enharmonicity constant is given by a formula. They generally give you the value of enharmonicity constant in the question, but if it is not given, then they will give you this dissociation energy, and this xe can be calculated from here. There's mu bar upon 4d. So this is the formula for it, and then Next point is the energy difference between two successive energy levels for enharmonic oscillator. So we have to calculate for n plus 1 and n level. So we can use our general formula for we have to place the value of energy in this form, that is it is n plus 1 level plus 1 by 2 nu bar minus, again this is n plus 1 level plus 1 by 2 square xe nu bar. In some books they can also use omega e bar for this nu bar, right? So you can use any of these two. Then we have to subtract the energy for n vibrational energy level. So it will become n plus 1 by 2 nu bar minus minus will become plus, and it is n plus 1 by 2 whole square nu bar xe. Now you can use this formula, open these equations and then simply subtract. This is the one way of remembering it. Another way, you can directly remember the formula of energy difference, and it is given by this nu bar minus 1 plus n 2 nu bar xe. So you can memorize this formula or this one. Any of these two can be remembered, but I would suggest that you remember only the simple formula. This is very easy to open these brackets and to solve this, right? Sometimes you cannot remember a long formula during the examination, so you can simply remember only one formula for energy, and then you can easily determine the difference between two successive energy levels. Then one more thing is that this d naught is equal to dE minus 1 by 2 h nu. How we can calculate it? This dE is the value of dissociation energy from this level to this level, and this d naught is started from 0 point energy level, means ground energy level, right? So we can, if we can subtract this part from this, right? So if I will subtract this value of energy from here, then I can get this d naught. So next point is the value of what is the gap between two successive energy levels. So in this case, in case of enharmonic oscillator, this gap will not remain equal. Why it will not remain equal? That suppose this is 0 point energy, for next level I have to place 1 here, right? So it will become nu bar minus 1 plus 1 2, 2 into 2 4 nu bar xe. For next level it will become 2 plus 1 3, 3 to 2 6 nu bar xe. So this level will successively decrease, this gap will successively decrease, right? Another way to understand it, that the energy is given by n plus 1 by 2 nu bar minus n plus 1 by 2 whole square nu bar xe, right? So if I will place the value of n, I have to subtract this part from this energy value. So this part, this n is continuously increasing, its square will also continuously increase. Then this negative part is increasing by square value, so this energy value will decrease when we go up in the levels, right? So this level will, this gap, this energy gap is continuously decreasing for enharmonic oscillator. So this is the biggest difference between harmonic oscillator and enharmonic oscillator, right? So you have to remember this part, that energy gap is decreasing, right? Then next is selection rule. For harmonic oscillator we have seen the selection rule is plus minus 1, but for enharmonic oscillator or for the real bonds, this selection rule is plus minus 1, plus minus 2, plus minus 3 and so on. Means if I will take this n is equals to 0, this is suppose n is equals to 1, this gap will decrease, it will become suppose n is equals to 2, These are the vibrational energy levels. So this plus minus 1 means, suppose we are taking only absorption part, so transition from 0 to 1 means change in the n value is only 1. So this is for harmonic oscillator, and it is also applied for Inharmonic Oscillator or real bonds, and this transition is called as fundamental vibration or fundamental transition. So this is your first fundamental vibration, FV, and then suppose I am taking from 1 to 2, this is your second fundamental vibration. Then next is your plus minus 2 means 0 to 2 transition, right? And this type of transitions are called as overtone. So this is your first overtone, and 0 to 3 it is your second overtone. So in real bonds or in Enharmonic oscillators, overtones are allowed, and their intensity is much weaker. Their intensity is 10 to 100 times weaker than fundamental vibrations, but they are allowed. And then combination bands. Combination bands are given by, they are generated when we are combining fundamental vibrations, 2 or more fundamental vibrations, and fundamental vibrations and overtones. Means suppose I am taking n plus 1 means first fundamental vibration and second fundamental vibration together. This is called combination band. We can take fundamental vibration and first overtone together, means overtone is just twice of this. So we can take overtone with fundamental vibration. This is also combination band. Then difference band is the band which is obtained after subtracting 2 fundamental vibrations and overtones, right? So this is all about harmonic oscillators and inharmonic oscillators. One more important thing is isotope effect. Isotope effect is very simple thing. It is similar to microwave spectroscopy. Then in this case the energy is given by, suppose I am taking here harmonic oscillator. So this is the energy value, sorry, this one, right, in centimeter inverse. So this energy is directly proportional to wave number, and the wave number is given by 1 upon 2 pi c under root of k over mu. Means wave number is inversely proportional to under root of mu. So we can say that this energy is inversely proportional to under root of mu. Now we can use this equation for different isotopes. So this part is very simple. This mu is nothing but reduced mass, and we know that reduced mass, this is given by m1 m2 upon m1 plus m2, right? So this part is very simple, and you can see questions based on this isotope effect in previous years questions. At the one question is also in December 2019 from this isotope effect, right? So that question was also very easy. Simply they have taken OH vibrations, and when we will replace this H by deuterium, then what will be the change in the vibrational frequency. So that question was very simple, that you have to just place the value of mass of deuterium in place of H in this equation, and you can calculate the change in vibrational frequency. Then next part is, that is very important, that is rotational vibrational spectroscopy, which is also called as a PQR spectrum. So what is the meaning of it? It means that when we are considering a vibrational motion, when we are giving a molecule energy sufficient for vibrational transition, then it is also possible that there will be change in its rotational levels. Means there is rotational motion, rotational as well as vibration in the molecule simultaneously. right? And according to Born-Oppenauer approximation, the energy is, these two energies are unaffected by each other, and we will get total energy by simply by addition of these two energy. What is my meaning? That according to Born-Oppenauer approximation, what they have said, that if we want to calculate the total energy of a molecule, and we are considering, suppose here, only two motions, vibrational and rotational, other energies are also considered in this approximation, but here we are taking rotational and vibrational energies. So according to this approximation, it is considered that total energy of a molecule is nothing but the simply addition of these two. Means we have to add only separately the rotational energy plus vibrational energy, right? These two energy will not interact with each other, there is no change in their particular values. We have to simply add these two to get total energy. This is this approximation. There is also the violation in this approximation, but we will consider only this approximation here, right? So how we will get total energy? Simply we have to consider the rotational energy and vibrational energy. So if I am taking this rotational energy by considering your non-rigid rotator, we have to consider the non-rigid rotator, because the bonds are not perfectly elastic in nature. There is change in their bond length when there is rotation due to centrifugal force, due to centrifugal distortion. So the energy is given by Bj, j plus 1 minus dj square, j plus 1 square. We have seen this formula, how we calculate this formula, how we can use this formula. We have seen this part in previous video. So if you have not seen that video, I will provide the link of that video in the I button. You can check that one. And the energy of Inharmonic oscillator is given by n plus 1 by 2 nu bar minus n plus 1 by 2 whole square nu bar xe. This is for Inharmonic oscillator. So the total energy of this PQR spectroscopy, or this rotational vibration spectrum, is given by Bj, j plus 1 minus dj square, j plus 1 whole square plus, right, this one. In this equation we can ignore this part, right, but we should not ignore it. This is also important because we are considering the real bonds, so we have to consider the distortion equation also. But if we are considering this, then the equation will become quite complicated, and if we can ignore it, there will be very little effect on the final spectrum, because the value of D is very small as compared to B, and this factor will become also very small because of this D. So we can ignore this part. The total energy is given by, so you have to remember this equation. This is very important. You can see this the questions based on this equation in GATE exam. This is very important part, right? Then what is the selection rule? Again the same. This for del n, this is plus minus 1, plus minus 2, plus minus 3, as in case of Inharmonic oscillator. That is again same. This is for fundamental vibrations and this is for overtones. And del j, this can be 0 for few bonds, few exceptions are there. Most of the time the change in z value is not allowed, it is forbidden. Most of the time it is forbidden, but few exceptions are there. And then plus minus 1, right? Next thing is, so we know that each vibrational level is consist of several rotational energy levels, right? So here we have two vibrational energy levels, N1 and N2, and each is consist of several rotational energy levels. And we know that in case of non-rigid rotator, this energy gap will increase, right? So we have drawn in such way, in that way. So in case of PQR spectrum, we have three type of possibilities. first is P branch. How we will get P branch? For P branch, the change in N value is plus minus 1 and change in J value is minus 1. Means if we are starting a transition from 1, then it will go to 0 value J. This will go from first J is equals to 1 to J dash is equals to 0. There is change in J value by minus 1, right? And so in this way there is change in the J value as well as change in the N value, change in the rotational energy level as well as change in the vibrational energy level also. So we can have this type of a spectrum in several ways, that if we are starting from J is equals to 2, it will go to J is equals to 1. If we are starting from J is equals to 3, it will go J is equals to 2. From 4, 5 to 4. Right. So this type of these branches are called as P branch. This spectrum is called as P spectrum. Then we can have Q branch. In Q branch, there is change in N value plus minus 1 and J value is change in J value is 0. Means this is forbidden. So most of the time we will get no spectrum in this Q branch. Next is R branch. In R branch, change in N value is again plus minus 1 and change in J value is plus 1. So if we are starting from J is equals to of this vibrational level, it will go to J is equals to 1. Change in J value is plus 1. And simultaneously there is change in the vibrational energy level also. So for next J is equals to 1 to it will go 2. From 2 to it will go 3. From 3 it will go 4. And from 4 it will go 5, and so on. So this is your R branch. So in P branch, we can calculate energy if we are considering your, suppose for J plus you have to consider the change in energy value, right? So change in vibrational energy level plus change in rotational energy level. So change in vibrational energy, n plus 1 nu bar minus n plus 1 whole square nu bar xe, and for rotational level you will consider only bjj plus 1. So you can calculate the difference between two vibrational and rotational energy level, and then you can calculate the total energy. And for Q, this is forbidden level, so we will not calculate its energy level, but you can say that it is pure vibrational motion. There is no change in the rotational energy level. This is pure vibrational motion. For R, again you will apply this formula, but this time the change in the J value is plus 1. So you have to consider these things. Then if we will draw the spectrum of these PQR branches, so suppose this is first P branch, this is second, this is third, this is fourth, and this is your fifth. Why I have drawn these lines of different heights? Because we have seen in microwave or in rotational spectrum that there is the highest intensity of spectrum at particular J value, at J max. So we can calculate the value of J max. We will also see that how we will apply J max in PQR spectrum a little bit later, but first you have to calculate the value of these lines in this way. Then this is suppose R, and this is suppose first line, this is second, and this is your third. There is a little bit change in PQR values, that this line is started from J is equals to 1, so we will denote it by P1. This part is very important, and this will become your P2, this is P3, this is P4, and this is P5. But in case of R, it is started from J is equals to 0, so we will denote it by R0. This is R1, this is R2, this is R3. So this point is very important, that this P is started from P1 and this R is started from R0, and this is your this point is called as your this point is called as bend center. This is for forbidden energy level. So I can draw these lines again here to understand it. So suppose this is your P1 and this is P4, then again the intensity will decrease, right? And this is your R0, this is R1, this is R2, and this is R3, and then intensity will decrease, right? And this is your bend center. This is for Q branch and for it is forbidden. The energy gap between these spectrum is given by 2B, and this is constant, right? There is slight changes in it, but most of the time it is constant. Similarly, this gap is also 2B, but this gap between these two levels is 4B. Between P1 to R0, this gap is 4B. So here we have few things which are very important, that for P branches the change in J value is -1. So I will denote these important point by different color, so you can remember. By -1 for R branch, the change in J value is +1. Change in N value is same for both of them, but change in J value is different. Then this gap is 2B for all of them. This gap is 4B. Then this gap between P1 and R0 is 4B. So this point is also very important. Then value of J max. J max means we are talking about that when we will get highest peak for P and R branch, at what J value, right? These are J values written here, 1, 2, 3, 4. From these peaks, from which J level these spectrums, these spectral lines are arising. Next is J max value. So first we will take for R branch. For R branch, it is given by under root of KT 2BHC minus 1 by 2. We have seen this formula in rotational spectrum also. This is for R branch. For P branch, this value is J max for, you can write J max P is equal to J max R plus 1. You can see here that I have denoted this maximum P intensity of P at P4, and for R it is R3, because I have started from R0, but this is started from P1, right? It means the J max for P will become under root of KT 2BHC plus 1 by 2. This formula, these two formula are very important, right? Then one more thing is here, that when we are doing vibrational and rotational motion simultaneously, this vibration will cause change in the bond length, right? And when there is change in the value of R, the I will increase, moment of inertia will increase, and we know that the value of B, rotational constant, is inversely proportional to I. So B will also change. So the B value will change when we are taking vibrational and rotational spectrum simultaneously. So we have to consider the change in B value in few numericals, and it is given by BV. BV means the rotational constant when we are considering vibrational motions also is equal to BE minus alpha E n plus 1 by 2, where VB is rotational constant when vibrational motions are there, and VE is rotational constant when no vibrational motion, right? And alpha E is rotational vibrational coupling constant, and its value is equal to 12 B E square nu bar. Okay, so there are very few questions on this formula, but you can remember it. In future you can have questions based on them also. Next we will take questions from CSIR NET and GATE. So first question is from GATE 2018 for a diatomic vibrating rotor, means they are considering vibrational as well as rotational spectrum. Vibrating rotor in vibrational level, this is the value of n. We can denote this n by this symbol also. And rotational level J, the sum of rotational and vibrational energy is given, its equilibrium oscillation frequency is given, and harmonicity constant is given, rotational under rigid rotor approximation is given, rotational constant is given, the value of J is. So they have written that rotational constant under rigid rotor approximation means we have to consider that there is no change in the B value during the vibrational motion. So what is given, that the n value, this is also denoted by this symbol, is given is 3, and the total energy is given 11493.6 centimeter. The value of equilibrium oscillation frequency, this nu bar is given, that is 2998.3 centimeter inverse. Inharmonicity constant, that is Xe, is given 0.0124, and this nu bar, this equilibrium oscillation frequency can also be given by omega E bar. You can use this symbol also for this. And rotational constant is B is given. So this question is very simple, only calculation is there. You have to just apply this formula. Et is equals to E rotational energy plus E vibrational energy. It is equal to Bjj plus 1 plus n, or I am using this symbol here for your convenience. So omega E bar minus, right? Now you can place all the values and you can calculate J value here. J is asked. So this question is very simple. You can easily calculate here and you will get the correct answer. Next question is from GATE 2020. Assuming no interaction between vibrational and rotational energy levels in HF, the frequency of R branch originating from J is equals to 4 in its spectrum is, what is the value of R branch frequency? So this question is little bit tricky. They have given us rotational constant and the value of nu naught bar, equilibrium vibrational frequency. This is little bit tricky, at the same time very simple also. First line, that assuming no interaction between vibrational and rotational energy levels, it means that we have to simply consider the Born-Oppenauer approximation, that we can have total energy value by summing up the value of vibrational energy as well as rotational energy. So you don't have to confuse with it, but simply draw the spectrum of PQR. What is the spectrum? That first, suppose I have P1 here, P2, P3 and so on. We don't need the P branches here. Then we have this bend center, and this bend center is denoted by this equilibrium frequency. Here they have used this term here, right? And then we have R branch, which is started from R0. Then we have R1, R2, R3 and R4, right? We don't bother with the height of the lines, but simply you have to consider the positions of these R values. So they are saying that R branch originating from J is equals to 4, means we have to consider till R is equals to 4. This gap is given by 2B, this is 2B, this is 2B. These all gaps are equal to 2b. This is the most easiest way to calculate solve this question. So all these gaps are 2b, and if you calculate from this nu naught to r4, the total gap is 1 2 3 4 5. 5 into 2b is equals to 10b, right? And what is the frequency? Means we have to consider this nu naught equilibrium frequency plus 10b till this level. So we will get the total value of frequency, where we will get this r is equals to 4. So this nu naught is given 413.852 plus 10 into rotational constant is given this one. So you will get your final answer by summing up this one. This is your answer. This question is very simple and very good also. Next we have question from NET June 2018. I think this question is not clear. I will read this question for you. Assuming harmonic approximation, the energy change for the reaction HCl plus D2 gives DCl plus HD in centimeter inverse. So we have to calculate the change in the vibrational frequency, and the vibrational frequency for each reactant as well as product is given. So we have to consider the formula that E vibration is given by n plus 1 by 2 nu bar, because they are saying that assuming harmonic approximation, we are considering that motion is simple harmonic oscillations. So we will consider this formula, and n value will be considered as 0. We will consider that this is ground state vibration. So the formula will become E is equals to 1 by 2 nu bar, right? So the change in the value of energy is given by the energy of product minus energy of reactant. So what is that reaction? That HCl plus D2 will gives us DCl plus HD. So we have to consider the energy of DCl plus energy of HD minus energy of HCl plus energy of D2. And how we will calculate this energy? By using 1 by 2 nu bar. So simply you have to place the value of frequencies. Frequency of DCl and HD, that is given by 1990 plus HD is 3627 minus 2885 plus 2990, right? So you can calculate this. This is very easy and you will get your answer. Then next question is very interesting, and this question is from June 2019. They have given us a plot between del G, which is given by the change in the vibrational energy with vibrational energy level, that is it is denoted by nu in this case plus 1, right? And this is given by a straight line, and the slope of the line is minus 14 centimeter inverse. Intercept is 2170 centimeter inverse, and the approximate value, they are asking us that approximate value of dissociation energy of CO is. So we have to calculate the value of D here, and the formula for D is also given, that is it is given by omega upon 4xe. The value of energy level of this inharmonic oscillator is also given. We have used the different terms in this equation, but we can denote it by this one also. Now this vibration energy level is denoted by this nu instead of n, and the frequency wave number is given by omega minus omega xe, right? So what you have to do, you have to calculate this change in energy value, that is given by del G here, right? And it will be calculated by difference of two vibrational energy levels, that is nu plus 1 and nu. So we have to apply this formula here. Nu plus 1 by 2 omega minus nu plus 1 by 2 square omega x e minus nu plus 1 by 2 omega minus nu plus 1 by 2 square omega x e for new vibrational energy level for this one, right? When you will calculate this formula, you will get directly this value, this one. We have used the same thing here. You can solve this equation or you can directly write down this value. So what you will get here, you can solve that one, and I am directly writing the value, that is omega minus 1 plus nu 2xe omega. You will get this one. Instead of writing n here, I have written nu, and instead of writing nu bar, I have written omega here. Only difference is this one. So you will get this type of equation here. You can compare this equation with the straight line equation, that is y is equals to mx plus c. Why I have written mx here? Because the graph is plotted between del g and 1 plus nu. 1 plus nu is your x. You can draw the graph like this. This is your del g and this is 1 plus nu, and the graph is with negative slope like this. It has intercept c value. This c is equals to 2170 and the slope is equals to minus 14. So you can compare this equation with the straight line equation. C is equal to, intercept is given 2170, so it will automatically become equal to vibrational frequency, right, in centimeter inverse, and slope is given by minus 14, so it will become equal to minus 2xe omega. You can compare with this equation. So what we will get, xe is equal to 14 upon 2 omega, that is 7 by omega. If you place the values of this one and this one in this equation, you will get the value of d, omega upon 4xe, omega upon 4 into 7 omega. Now you can solve this value and you will get your answer, right? Correct answer will be third. You can calculate this one. Next question is also from June 2019. That is the correct statement about HCl and DCl among the following. DCl has a smaller 0 point energy than HCl. So first we will write down the formula of 0 point energy, or this one, and it is equal to omega is inversely proportional to your under root nu. So DCl will have higher nu value than HCl, that is why the omega value will be smaller for DCl. Automatically your energy, 0 point energy, will be lesser. So first point should be correct, but we will check other one also. HCl has a smaller vibrational frequency than DCl. This is wrong, right? Then third is the force constant K of HCl bond is half that of DCl. We cannot say this point directly from this equation. So fourth one is the reduced mass of DCl is smaller than that of HCl. This is wrong because reduced mass is m1 plus m2 upon m1 plus m2, m1 m2 upon m1 plus m2, and the mass will be higher for D. That is why it will be higher for DCl. So answer 1 will be correct answer, right? So this is all about this chapter. I have covered all the important points of vibrational spectroscopy as well as PQR spectrum. So I hope this video will be helpful to you, and if this video is helpful to you, please share my videos with your friends Thank you so much for watching.